Let's take a look at another example of the method of maximum likelihood, and let's fit a Weibull distribution. Now, we didn't talk about a Weibull distribution a great deal in class. However, this is a good example of fitting a probability distribution because it has a little bit different feel to it. It has two different parameters, and it just lends itself for the method of maximum likelihood. Okay, so again, what we're going to do is evaluate this Weibull distribution PDF. It has two parameters, beta and theta. We're going to evaluate that PDF for each one of our failure time observations. Let's say we have 35 observations of failure time, and so we're going to evaluate this PDF given a couple of different parameters, and we're going to have to estimate those, beta and theta. And let's just guess for beta. Well, remember that a special case of the beta distribution is the exponential distribution when beta is 1. Let's just assume 2. Okay, beta is not going to be a very big number. And then theta is going to be somewhere around the mean of all of these observations. Okay, I just happen to know that because I've dealt with the Weibull distribution before. So I would choose, because again of this background knowledge, something that looks similar to the mean of all of these observations. Let's just say that's 50 or so. Okay, so we've now got our starting points for the optimization. Okay, and plus we have to include these values to get at least some estimate of the PDF for each one of these observations. Okay, so now let's implement this equation. We've got beta times y raised to the beta minus 1. Okay, and we should probably put a paren here and here. And you can never be too cautious with your parentheses in Excel. Then we're going to divide that by theta to the beta. Okay, so we've got that out front. Now we're going to multiply that by the exponential function, negative y divided by beta raised, pardon me, y divided by theta, excuse me, theta raised to the beta. Okay, and we want to be careful here about the negative in this exponent. Okay, again, you can never be too cautious. Let's include that here, and then one more to close out the exponential function. Okay? Okay, so this should work. Okay, so that is the PDF evaluated for failure time of 1.3 time units when these are our beta and theta values. Okay, so now again, just like before, we want to drag down here. So we need to put dollar signs in front of the H's and in front of the rows 1 and 2. Okay. One shortcut for doing this is if we just put the cursor inside the cell that we want dollar signs in front of, and then just hit the F4 key. That doesn't seem to be working. I guess that doesn't work. Not for this computer. But generally speaking, that would work for you. Okay? We've got to put dollar signs in front of the row and the column for each one of these H cells. And of course, we want the B column to be able to roam free because we want to evaluate this PDF for each one of these values. Okay, so then we can just drag down, double click on that cross, and we've got all of these values. Okay, and just like before, rather than multiplying all these values together, let's just go ahead and take the natural log of these now. Okay, so let's take the natural log of the PDF, evaluated each one of these observations, and then sum those up. Okay, great. So now let's take the natural log likelihood function. That's the sum of all of these values. And remember again, what we want to do is maximize the natural log likelihood by changing the values of beta and theta. So we're going to go to the data tab and the solver function. Okay, and we want to set our objective as this cell right here, the natural log likelihood. We want to maximize it by changing the values of beta and theta. Okay, we're going to use the evolutionary algorithm again, and what we need to do here is put bounds on the search space for beta and theta. So for beta, let's say that it is going to be greater than, let's say 0. Okay, that needs to be a positive number, or a non-zero number. It needs to be a positive 0 or greater. It needs to be 0 or greater. And we're going to set an upper bound on beta to be, let's say, 3. Okay, beta is going to tend to be small. And then for theta here, let's set a lower bound. Set a lower bound of let's say 30 or so, and we'll set an upper bound. Sorry, this is going to be the lower bound, 30. I thought I was doing that wrong. Let's go back and fix this. That's going to be, let's say, an upper bound of 100. Okay, so now we have our objective function, the cells that we want to change. We have constraints on those cells, lower and upper bounds for each one of those, and let's implement the evolutionary algorithm. We'll let it run for a little bit. You probably don't need to let it run too long. We'll hit escape to stop it. And we find that the optimal values, or at least our approximation of optimal values for beta and theta, would be 1.39 and 58.55. Okay, so using the method of maximum likelihood, the values of beta and theta that maximize the natural log likelihood function, which is the same as maximizing the likelihood function if we were to multiply all of these together, those values are 1.39 and 58.55. Again, can't stress this enough. This is not an analytical solution. We're using an approximation algorithm. Okay, sometimes finding the analytical solution to an optimization problem, using calculus, for example, is a difficult thing to do, a difficult task. For this task, that might not be so straightforward. So using an approximation algorithm is important in this case. Okay. So that's what we've done here. We've used an evolutionary algorithm. You can read up more about the evolutionary algorithm and how the solver function works by taking a look at the help function, by searching the internet to find more information. But this is a basic introduction to how to implement the method of maximum likelihood using the Excel solver.